Hello everyone, my name is Sarbhat Pratik. I'm a master's student at University of Southern California in Los Angeles. I'm excited today to present our work titled Optimizing Human Activity Recognition for Constrained Environments Using Random Forest and Feature Subset Selection. This is a research by Kunal Goyal, Shreya Goyal, and Sarbhat Pratik, that's me. In this research, we have addressed the challenge of running human activity recognition on devices with limited computing resources. Our approach uses a random forest classifier to identify and select a small subset of the most important features, which dramatically reduces the data processing and the computation required for HAR while still maintaining high accuracy. Introduction. So, human activity recognition is the task of classifying human actions from sensor readings. In our context, we focus on wearable and smartphone sensors that capture motion. HAR has a wide range of uses, for example, monitoring patients in healthcare, improving user context in smart homes, and tracking workouts in fitness apps. Over the years, researchers have developed accurate HAR models. But the challenge now is that many state of the art models are very complex and are resource hungry, often involving large neural networks. These achieve high accuracy but are impractical to run on small devices in real time. This sets the stage for our work. We need HAR solutions that are both accurate and efficient for on device use. Our challenges. So, why is on device HAR challenging? Simply put, resource constrained devices have limited CPU power, memory, and battery life. A complex algorithm that runs fine on a server might be overwhelmed when run on a smartwatch. Heavy computation will always drain a device's battery quickly. Moreover, for HAR, we want real-time responsiveness. For instance, instantly detecting if someone falls. Limited processing power makes this difficult if the model is not optimized. Connectivity is not always available or desirable due to privacy, so offloading it to the cloud is not a viable option in many cases. Thus, the key challenge is achieving high recognition accuracy under strict resource limits. We need to simplify models and reduce data so that HAR can run continuously on a phone or a wearable. In prior work, others have explored simpler models and feature selection techniques to make the HAR more efficient. While deep learning approaches often achieve the best accuracy, they demand significant computation and large training data. Researchers have found that selecting a subset of the most relevant features can maintain high accuracy with far less complexity. For example, Thakur et al. 2023 applied a regularized random forest to pick key features and still achieved approximately 99% accuracy on a smartphone HAR dataset. This demonstrates that we can greatly reduce the input dimensionality with minimal performance loss. Our work builds on this idea. We are going to use a random forest to identify the important features and emphasize a solution that is lightweight enough for an on device deployment. Dataset. So, we have evaluated our methods on the popular UCI HAR dataset. This dataset contains sensor data collected from 30 volunteers performing 6 activities, which were namely walking, walking upstairs, walking downstairs, sitting, standing, and laying. Each person wore a smartphone on their waist, which recorded accelerometer and gyroscope signals at 50 Hz. The data was segmented into short time windows, approximately 2.5 seconds each, and each window is labeled with that activity. Importantly, each window is represented by a 561 dimensional feature vector that includes a variety of time domain and frequency domain features extracted from the sensor signals. This comprehensive feature set makes UCI HAR an excellent testbed for feature selection because it has more features than necessary, which gives us room to simplify our model. Data preprocessing. Data preprocessing. We performed standard preprocessing on the dataset. Since UCI HAR is well prepared with almost no missing values and predefined training test splits, our main steps were to format the data and normalize the features. We scaled the features using standardization techniques so that all the features are on a comparable range, which can help the learning algorithm. We also ensured that the training and test sets were kept separate during preprocessing to avoid any data leakage. In summary, the data set was clean and ready, and after normalization, we could proceed directly to model training. Feature extraction. So, in this work, we did not perform new feature extractions. We leveraged the features provided by UCI HAR. UCI HAR. The 561 features include a broad range of descriptors derived from the raw signals. They cover simple statistics, mean, standard deviation, etc., as well as the more complex features like signal energy, frequency domain coefficients, correlations between axes, and so on. In essence, these features comprehensively describe the motion in each time window. Our goal was to determine which of these features are actually necessary. Rather than dealing with raw accelerometer readings directly, we took this rich feature set as input and focused on trimming it down to the most essential components. Our random forest classifier. So we chose random forest as our classification model and as the tool for feature selection. A random forest is basically an ensemble of decision trees that votes on the output, and it's known to be effective for HAR tasks while remaining relatively efficient. One big advantage of random forest is that it provides an important score for each feature after training. This tells us which features the model found most useful. In our experiments, we trained a random forest on the full 561 feature dataset to serve as a baseline classifier and to obtain the feature important rankings. This baseline model gave us both a high accuracy reference and a ranked list of features by importance, which is exactly what we needed to guide our future selection process. Our feature importance. The random forest's output confirmed that the feature importances are highly unevenly distributed. A small number of features turned out to be extremely informative, while others had negligible importance. For instance, features related to the magnitude and variability of acceleration were among the top ranked. In contrast, some features, like certain angle measurements or derived metrics, had nearly zero importance. This suggested that a lot of the data in the 561 dimensional space is redundant or irrelevant for the classification task. In practical terms, this finding indicated that we could remove a large number of the lowest important features with minimal impact on accuracy. It sets the stage for our feature reduction experiments. Our experimental workflow. Our workflow proceeded through several steps to evaluate feature subset selection. It was to train a random forest using all 561 features and record its accuracy on test set, then rank all the features by their importance scores from the trained random forest, And we also implemented top k scores. For various values of k, we trained a random forest using only the top k most important features. Then evaluating performance, we measured the accuracy of each reduced feature model on the test set and compared it to the baseline. Then we identified the optimal subset, where we determined the smallest feature subset that achieves an accuracy nearly to the baseline one. This procedure allowed us to systematically explore the trade offs between the number of features and the model's accuracy, and to find an operating point that is much more efficient than the full model. The baseline results. So, first, the baseline. We used all 561 features. Our random forest achieved about 96% accuracy on the UCI HAR test set. This is in line with reported results for comprehensive models on this dataset, confirming that our implementation is performing well. However, this baseline represents the most resource intensive approach since it uses every feature available. It's like the upper bound on accuracy, and not just that, it's also the upper bound on computation. So the main question we posed was, can we get an 96 can we get almost 96%, 98% accuracy with far fewer features? Feature importance insights. Analyzing feature importance scores revealed that a small subset of features dominated the model's decision making. Many features had near zero importance. Key features included energy and standard deviation of body acceleration signals, frequency domain energy components, mean frequency, and angle based motion features. These findings suggest that the model can rely heavily on only discriminative features, offering strong potential for dimensionality reduction with negligible performance loss. The dimensionality reduction results, the accuracy versus number of features. Our model with all 561 features achieved 98%, 98.88% accuracy, and when we took just 50 features, the accuracy was 98.54, which is just a 0.34% drop. With 20 features, it was 97.73, and with 10 features, it was approximately 95.79. These results indicated that over 90% of the original features could be discarded while preserving most of the performance, and this was significant for reducing the model size and computation without major loss in classification power. Practical implications for our embedded HAR systems. Reducing features while maintaining high accuracy benefits HAR deployment in constrained devices. Faster inference time on mobile CPUs, lower memory usage and battery consumption, simpler and cheaper sensor configurations, and easier to implement in real time applications. Our feature selection method enables HAR systems to operate efficiently and accurately on embedded platforms with strict resource limits. Conclusion and future work. We showed that random forest based feature selection can drastically reduce the number of features required for high accuracy HAR, retaining only 50 out of 561 features, preserved 98.54% accuracy. So, the key insights are that dimensionality can be reduced by 90% with minimal loss. Selected features were interpretable and linked to body motion patterns. And the future work for us would be testing across new data sets, real time implementation on mobile hardware, and adaptive selection techniques for dynamic sensor inputs. So, thank you guys. That was all. And hope you have a good day.